Good evening to everyone. So today it's my privilege to introduce Professor Sri Krishna Ghoshal. Professor Sri Krishna Ghoshal obtained his PhD from the Jawaharlal University, Delhi, India. He was a postdoctoral fellow at Brandeis University, USA, IIT Delhi, and Oxford University, UK. He has published over 650 research articles in international reputed journals, 19 book chapters contributed by him, and 7 books he has written. With Google Scholar H index 47, he is earned by him, and I-10 index of 160, and citations 7,994 number of citations of his research. He received 58 number of research grants, 2 patents on proposed anti-cancer drug formulation and plasmon humidity sensor. He has supervised 30 PhD theses. He was recognized as among top 2% of the scientists in their field worldwide by Stanford University, USA rankings. Very nice achievements by him. On the behalf of all the RIO's members, I welcome you, sir, Professor SIB KRISHNA Ghoshal, to this webinar. Now, I kindly request Professor SIB KRISHNA Ghoshal to begin his presentation on the topic is biomedical facets of fluorescent plasmonic silver copper core cell nanoparticles. Welcome, sir. Please start the presentation.
In this particular lecture on biomedical facets of fluorescent plasmonic silver copper core cell nanoparticle, I'm going to demonstrate how these nanoparticles are becoming a significant part of various technologies for the future. Not only just for biomedicine or biomedical or therapeutic agent, also for environmental monitoring, sensing technology, food technology, food processing, cosmetics, and various other technological development. Before I proceed with the technicality of the talk, in general, I would like to tell that this kind of research is driven by industrial need. As we have seen in recent COVID pandemic, the whole world great minds work together. Even then, we could not prevent. Mask after mask, vaccine after vaccine, antibiotics after antibiotics, pills after pills, everything came in the market, but the virus kept on acting and made us ascend, and we finally realized how small we are even in the technological development. The virus left in its own, finally. Now the question is, it is a great threat to the humanity. The way infectious diseases are spreading all over the world at present time, the climate change, food crisis, environmental pollution, wildfire, all these needs great technology, efficient technology. And behind all these technology, high performance nanomaterials are needed. That's the most important thing, where optimization of the nanomaterials production, optimization of their properties are essential. Why we talk about nanoparticles of different kinds? I call this as 4 legs of the table. Number one, these nanoparticles are the main part of miniaturization of the devices. So we need less materials, efficient device. As we have seen yesterday from Professor Sriram talk regarding the Chandrayaan success, the whole device was full of several complex sensors. So all these sensors in some form, they need nanomaterials. Now, what are the kind of nanomaterials at present we are using for various technologies, particularly for biomedicine? Mostly transition metal oxides, rare earth metals, pure noble metals, all this. Now, if we look at the biomedical facets, what do we exactly mean by biomedical facets? It can be in the form of antibacterial or antifungal, antiviral, in general, antimicrobial ointments, can be lotion. Even we can put this nanoparticle on the mask coating, on the surface. Even we can put in the children's toy, water bottle, computer mouse, everywhere, washing machine, sanitizing tiles, car windows, everywhere, this kind of nanoparticles are needed. So this kind of research we have chosen to make some kind of antibacterial ointment, antibacterial surface, antibacterial pills, many things you can make from these nanoparticles. And this research has 2 parts. One is to look at the antibacterial properties of these nanoparticles, whether it can be in the clinical bedside tomorrow after successful application. And the other part is the production and characterizations of this nanoparticle. Now, 2 kinds of nanoparticles we have used here, combined them. One is silver, as you can see in the diagram in the left-hand side. So we start from the pure copper slab. We start from pure silver solid slab. Then we make nanoparticles using pulse laser ablation in liquid technique. Then we characterize this nanoparticle. Now, in the characterization, the Raman spectroscopy play a very significant role. And as we all know, nowadays, the SARS, which is called surface enhanced Raman scattering, TARS, tip enhanced Raman scattering, using these novel nanoparticles, we can make very high resolution measurements. In fact, parts per billion measurement in various biological samples. So the characterizations of the materials is important, equally important with the production. And then it goes through various characterizations technique as usual for every material. We need to look at their purity, stability, nanocrystallinity, their fluorescent properties, surface plasmon resonance properties. After it qualifies all these properties, then it goes for the applications. So this is the biomedical facets. Once this material qualify the essential properties, then we can use them in the washing machine, in the mask, in the ointment, making the pill, making injection, antibiotics, syrup, and various other products. Here, I just show schematically how these nanoparticles are produced. We use the target inside the liquid, deionized water, separately. we use silver target and copper target. This target with nanosecond Nd:YAG laser pulse through a mechanism called cavitation bubble formation, plasma plume. These nanoparticles are dispersed from the target inside the liquid, and we get the colloidal solution. And then we mix this silver and copper's colloidal suspension to form the core cell nanoparticles. We need to also verify whether they are really core cell, or they are nanohybrid, or they are nanocluster. So this is also another part of the game. And then after these nanoparticles are characterized, their properties are optimized, we choose the best nanoparticle, then apply on the bacterial strain, and look at the death of the bacteria over time by optical density measurements, by inhibition zone boundary measurement. So one is the biomedical aspect of this nanoparticle, and other is the physical properties determination of this nanoparticle starting from the production. Now the question is, why we want to produce nanoparticles? Is it only the inorganic nanoparticles like silver and gold? Not really. It can be organic, inorganic. For example, we are also working on cinnamon copper, cinnamon silver, cinnamon titanium, cinnamon gold, because we know cinnamon is from ancient time, cinnamon is used not only for spices and beverages, it is also used as medicinal in hot water for anti-coughing, anti-scar, and various other applications. So we also use organic and inorganic nanoparticles. Now the idea is when we go into the nano phase, we can control their density of states, electronic density of states. Now, by controlling the electronic density of states, we can create various kind of surfaces, various kind of morphologies. And these different types of morphologies, different types of densities of states are responsible for different application, different properties of this. One of such thing is the optoelectronic properties. As we know that depending on the size of the nanoparticle, as we grow smaller size, then and also with more tiny surface, large surface area, we can use them for different optical application because they need different light, starting from the red to the violet region. So this is the main thrust of this experiment, that how to modify, how to control, how to customize the density of states of the material. So in recent years, tremendous investment all over the world in different labs to produce nanoparticles after nanoparticles, because these nanoparticles are efficient, they are high performance, they need little material, so we need not have to use large amount of material, so the cost can be minimized. And when the production also require less material, so therefore chemical industries are not needed, so nature would be more protected. So green technology can be developed. So if you look at these metal nanoparticles or transition metal nanoparticles, either in their pure form or their oxide form or their nanocomposite form like core cell or nanohybrid, large number of applications are coming up. In fact, every day, newer and newer dimensions of application. Plasmonic mediated nanosurgery of cells, this is biomedical. Plasmonic based color encoding, nanofluidic solar system generation, surface enhanced fluorescence, surface enhanced Raman spectroscopy, plasmonic enhanced photovoltaics, multiplex bioimaging, and various other engineering applications of these nanoparticles. Now, question is, why these nano composites or core cell nanoparticles are so powerful? Because if you look at the bulk counterpart of this nanomaterial, they are less bioactive and bioavailability is also less. For example, if we put 2 cinnamon stick in a cup of water, hot water, and drink it, the effect we get for coughing, if we produce little nanoparticle of this cinnamon inside the hot water in some form of herbal product or some form of syrup or some form of pill, the impact would be order of magnitude different. So because these nanoparticles shows unique physicochemical, optical, electronic, and magnetic properties, so we can use them for different applications. For example, removal of heavy metals from wastewater. So wastewater treatment, water purification, air purifier, all these require. Not only this, as we know nowadays, if we enter in a corporate sector office, inside the airport, inside the supermarket, everywhere sensors are chasing us. Position sensors, movement sensors, gas sensors, humidity sensors, thermal sensors recording your temperature, breathing sensors, whether you are having influenza or flu or COVID in the body. So all these sensing technology, miniaturized sensing technology, high performance detection technology require these nanoparticles. And not only that, these nanoparticles have a very special property. They are less toxic and they are biocompatible. So important thing, when it comes from human use, it should be biocompatible and it should be also less toxic. At the same time, they should have environmental responsibility. They should be available, affordable, and also durable. So if we look at all these properties, then these properties contributes to the development of these biomedical facets. And that's where the research in this kind of core cell nanoparticles become important. So as I pointed in the beginning, these nanoparticles has to be produced by very efficient method. The morphology of the nanoparticles must be tailored or customized by varying the parameters of the method. These nanoparticles has to be produced at mass scale, large scale for commercial applications need. Now look, small industries cannot always afford on buying these nanoparticles expensive. They are very expensive. If you look at few grams from Sigma Rich or from Marek, if you order this kind of nanoparticles with stability 1 year, with nanoparticle size distribution between 25 to 40 nanometer, 8,000, 10,000, 40,000, 50,000, depending on the nature of the nanoparticle, is the cost in terms of dollar. Few $1,000s, few gram. So now the question is, if we can develop indigenous technology using lower cost of production and can create this material at cheaper cost in a homegrown way, that would be a great relief. Then we can save a lot of foreign revenue. So that's basically the idea of sharing this kind of research so that small lab, small research laboratory can start and produce the product locally. And that would be very useful for our future sustainable development. Now, what are the key attributes of these core cell nanoparticles, copper and silver, that we are producing? One is, of course, the size. Can we control the size using laser ablation technique? Now, first of all, why we use laser ablation technique? The reason is most of the other techniques need chemical precursors, like chemical techniques and many other techniques. Either they are size control is not that perfect, or these chemical precursors are very hazardous for human health. So therefore, how to get rid of these chemicals and more rely on the green technology. So laser ablation technology is that technique where we can use it without any precursor, without any extra chemicals. So therefore, we can use them for direct human application. And these nanoparticles, because their biocompatibility and less toxicity, they are very useful, and their stability is also very important, so we can use them for a long time. And they are, at the same time, environmentally responsive. Now, they have various characteristics, but the characteristics, as I told you, magnetic, optical, of course, every material will be having different characteristics, but the characteristics we are interested in, plasmonic. That's why we are using novel metal nanoparticles. We know silver is biocompatible. It is best plasmonic metal. And if we make the nanoparticle and control the size from quantum dot to nanometer, 10, 15, 20 nanometers, their plasmon is very strong. And this plasmon can be used for antibacterial, antifungal, antimicrobial, antiviral application. And when this plasmon with fluorescence I yield, the fluorescence properties is the emission of pure color. This color can be controlled, and this radiation in the form of electromagnetic wave can be an enhancing factor for the creation of reactive oxygen species. That's the important, that's the catch, that's the game. That plasmon and fluorescence together is responsible for response, strong response. And this response can be useful for the creation of reactive oxygen species. And these reactive oxygen species will be responsible for the damage of the protein and the membrane in the bacteria and virus. And that is the way it will act as antibacterial agent. So the sizes of this nano core cell structure or nanoparticles, we general nanotechnology say 10 to 100 nanometer, but the nanoparticles we produce is from 5 to 25 nanometer mostly. So they are very effective for this application. They have high fluorescence, they are biocompatible, they are stable, and they are low toxic. Now, these nanoparticles in general are highly beneficial. And we are not only, as I said, not only working on these nanoparticles, but today I have chosen this specially because we got some new interesting result that I want to share. However, we are also using for other applications like environmental, humid sensing, anti-cancer, and all other development. Now, specific applications we are also trying to use for optoelectronic applications, some for energy storage, supercapacitors with graphene coating, and so on. Novel medical devices, personalized medicine, for example, medical kits, sensors, for example, different types of sensors we are using these nanoparticles for gas sensors, petroleum detection sensor, many other purpose. So here is the experimental design of this method. Everywhere, whoever is having this laser, Nd:YAG laser in the lab, pulse Nd:YAG laser, you can develop this technique with very little investment. That's the purpose of my talk. I am trying to direct this that new research can be done without big investment, as Sir Raman did. He used to bring filter paper from Sweden and so on, that time, to purify benzene and to purify different chemicals to see the anti-Stokes and Stokes line. But today we are in much more advantageous position. Technology is very expensive, but using the lesson he has given to us, we can use that technique to make our material even at cheaper cost. That's the idea of this kind of research. So if we use this kind of laser and ablate the target with the pulse, then it will create inside the liquid high pressure region, cavitation bubble, then shock energy wave will be induced, they will burst, then thermodynamic equilibrium, statistical equilibrium will bring finally the nanoparticles in the solution. And here is the mechanism how the cavitation bubbles are formed the moment laser pulse go and hit the target material, whether it is silver, gold, or any other target. And then finally, we take this liquid sample where the nanoparticles are suspended. Then we do the bio-TEM. What you are seeing in the right-hand side is the transmission electron microscopic image. And here you can see these black blobs as the nanoparticles. Their sizes vary from 1.9 nanometer to 8.1 nanometer. This is one of the realizations. We have also produced different laser energy. So the question is, I can customize this nanoparticle by controlling various parameters: laser energy, pulse durations, pulse frequency, the distance between the lens and the target, the nature of the liquid, the pH of the liquid, electronegativity of the liquid. We can use methanol, ethanol, citric acid, honey solution, any other biocompatible liquid that can be directly used for medical applications. Now, here are the characterization I have shown you in two pieces. In the left piece, we are showing various characterization results, starting from the transmission electron microscopic image, how the nanoparticles are uniformly distributed inside the solution, and then they are pure by EDX, energy dispersive X-ray. We can prove that they are the pure nanoparticle without any contaminants. We can also see their size distribution by image J processing software. We can calculate that. We can also do EDX mapping to show their distributions inside the solution. We can also see FFT, selected angle electron diffraction, single lattice fringe profile to prove they are indeed the highly crystalline nanoparticles. And this crystallinity is a major factor for the antibacterial applications. And then we can also see the X-ray diffraction to show whether they are really the silver peak or the copper peak. So these kind of characterizations, high resolution techniques, are essential, because when it comes to the human applications, one has to be very careful. And that's why. Now, when we mix these two nanoparticles and then form the core cell nanoparticles, then we see that in their individual phase, the properties, and when we combine them, the properties are much more improved, much more modified. And that's where we need the hybrid nanoparticles. Many people call it nanocomposites, but we call it silver copper core cell because of when we measure the zeta potential, then we see here is the measurement of the zeta potential. Zeta potential tells us how stable these nanoparticle surfaces are. And as you can see, we produce silver nanoparticles which are zeta potential negative. When you produce copper nanoparticle zeta potential positive as a function of different laser energy, laser fluence, 5 samples we produce here each. And then when we combine them, as you can see, that the core cell nanostructure, core cell nanoparticle has zeta potential negative. This clearly indicates that the copper nanoparticles are at the core of the whole nanostructure, and silver nanoparticles are sit outside surface, which are forming the cell. So that's why we call it core cell nanoparticles. And these core cell nanoparticles are extremely useful for the antibacterial application. Now, how do I know these nanoparticles are having very strong optical properties? Say they have strong optical absorption properties. Here you can see the absorption spectra of this nanoparticle, and in the naked eyes, we can see their color. As we change the size of the nanoparticle, as we change the laser fluence, the size of the nanoparticles changes. So we can see the localized surface plasmon resonance peak tuned from 595 nanometer to 403 nanometer. So this is from the green to the purple to the bluish end. So based on the size, we can create different types of color, different types of surface plasmon resonance in this particular nanostructure. Now, if we look at the localized surface plasmon resonance absorption of the core cell nanoparticles, here you can see how their strong peaks are into different places. For example, for the core cell nanoparticles, they show two strong peaks, one at 402 nanometer, other at 560 nanometer. And both these peaks we can use for different applications. And then we measure their fluorescence lifetime, because lifetime decay measurement is very important for the fast response devices, particularly for sensors, fluorescence, plasmonic sensors. This is important. At the same time, we must look at their fluorescence quantum yield, because quantum yield will determine how efficient these nanoparticles in killing the bacteria, how efficient these nanoparticles for anti-therapy, for the therapeutic application, for the antifungal, antiviral, antibacterial application. So when it comes to the human applications, this should be more efficient. So that's why I call these nanoparticles are high performance nanoparticles. As you can see also, the mean size of the optimum sample that we produce at the laser fluence of these nanoparticles are having size around 7 to 8 nanometers, 7 to 7.5 nanometer, 7 to 8 nanometers. So these nanoparticles are highly effective for various, and here is the optimum laser fluence for this production of nanoparticles, 14.15 joule per centimeter square is this. And when we look at their PL spectra and FTIR spectra, we also see how the different light emission and how the different structures, where is the hydroxyl ions are around the nanoparticles. And as we know that most of our biological systems, body fluids are the aqueous solution. So if we produce these nanoparticles, we can directly transfer to the medical application without having any problem. When you look at the Raman spectra, as I say you, Raman measurement is most important measurement for these applications, So if we look at the Raman spectra of this nanoparticle, then we see that silver oxide modes are there because the material is in the water, so oxidations will happen. So silver oxide is a very good semiconducting optical band gap, which is a very good antifungal and antibacterial agent. So this is pure silver oxide mode. We are also having the water molecules around these nanoparticles. When we go to the copper nanoparticles, we also see copper oxide modes. And these two modes combined together in the silver copper core cell nanoparticles will be very useful for the creation of reactive oxygen species. And again I tell, the creation of more number of reactive oxygen species is the main game of this research. By controlling the fluorescence quantum yield and by controlling the color purity. Now, when we look at the color purity, where this emission is exactly happening, where this surface plasmon resonance is exactly happening, we need to do the CIE chromaticity mapping, which is CIE chromaticity diagram. As you can see in the right-hand side, that the CIE chromaticity diagram tells us 3 dots are in the blue-purple region. And this pure color, blue-purple region, is the highest frequency for these nanoparticles that we can use for the therapeutic applications, for the antibacterial and antimicrobial application. And here we directly apply these nanoparticles, optimum nanostructures, optimum core cell structure, apply on E. coli virus. We have also E. coli bacteria. We have also applied to other 3 bacteria recently. And we have found that these nanoparticles can easily penetrate because the size of the nanoparticles is much smaller than the membrane perforations in the bacterial cell, so they can easily penetrate. The moment they penetrate the bacterial cell, they can go inside and attack the protein, create the reactive oxygen species, and they can rupture the protein and the DNA inside the bacteria. And that is the way they can kill the bacteria, and these nanoparticles are very, very efficient for killing the bacteria. How do we know they are efficient? We go for further measurement called inhibition zone boundary measurement. This is the biomedical measurement, standard measurement technique, where we measure the optical density as a function of time. And in the downward, you can see on the Petri dishes, these bacterial cultures are there, E. coli culture, and we put drop-wise. We have 5 samples, we put drop-wise. So pure E. coli, we measure the optical density. Deionized water, we measure the optical density. We measure the optical density for our 5 samples that we produce at 5 different laser energy. And you can see here that with time and with the improvement of the size of the nanoparticle, when we reach to the optimum nanoparticle, which is the S4 and S5 sample, you can see bacterial growth is totally hindered, and the bacteria is totally wiped out from the culture. And this is the proof that these nanoparticles, these core cell nanostructures, are highly efficient for the antibacterial application. So these novel silver, copper, core cell nanoparticles, or any other combination of these with organic nanoparticles such as turmeric, such as mint leaf, curry leaf, cinnamon, clove, black pepper, cardamom, we are trying to get different combination. We know them that during the COVID time, everyone recommended us to take the vapor of clove, vapor of cinnamon, drink cinnamon, ginger, all these ginger shoot. These we can use and make different types of nanoparticles. So these kind of facets, these kind of multi-purpose application, various diverse applications, newer type of applications, by controlling their quantum size, by controlling their quantum properties, density of states, by controlling, optimizing the laser parameters, also the liquid, nature of the liquid, pH of the sample, the purity of the sample, we can create a lot of biomedicine, and that we call nanomedicinal application of this kind of So these, in short, these types of nanoparticles, organic, or organic, inorganic, especially noble metal nanoparticles, because they have strong surface plasmon, as we know. At the same time, they are having also the antibacterial and biocompatible properties we can use for gene therapy, cancer therapy, diagnostics, sensing technology, biomedical. We know during COVID time, gold nanoparticle played a very important role for the COVID detection. Copper and silver nanoparticles were sprayed on different surfaces to protect, to hinder the growth of the bacteria, to hinder the growth of the virus, to hinder the growth of the antifungal fungus. So all these nanoparticles can be used for surface application, not just for killing, for retardation of the growth, for wiping them out under mild UV or even under solar radiation. They can be very active. So these materials can be used as a sensitizers for surface application. So material science at present is going towards a new functional materials, man-made materials, where natural materials are no more efficient. So we need to look for newer type of man-made materials. Metamaterials is one such. Negative refractive index material is one such material, which we call sometimes smart materials for space applications, for sensing application, for various kind of personalized devices, portable devices, even for artificial intelligence, digital economy. Everywhere you go, you need to use sensors. And these nanoparticles can be used for the development of sustainable and miniaturized sensors. So in conclusion, I just would like to tell that we don't need big investment. Using cheaper technique, by using careful administrations or executions of the experiment, we can produce locally. A lot of research we can do. There are great openings, even in the college, even in the school, even in the universities, where big investment is not possible, where government asks for the generation of income. Small industries can come forward. They will invest little money, and this is the way industrial growth can take place. In Malaysia, the government and university always look for this kind of industrial collaborations. With little arrangement, you can do plasma processing of material, plasma processing of food security, for example, how to clean the food, how to clean the food using the plasma, seeds, for example, palm seeds, wheat seeds, rice, all these we can do using nanoparticles, using different kind of sensing technology, and so on. So these nanoparticles that we used are highly fluorescent nanoparticle. They have short fluorescent lifetime. Their morphology and structure can be well controlled using the laser ablation technique. Laser ablation itself is such an interesting, such a beautiful technique where we don't need any chemical precursors. So green technology, eco-friendly technique, here is the game. So we can therefore protect our nature. We don't need natural resources much. We need not have to pollute the environment. We need very little. That's the idea of doing this research. So we can use them for biological imaging, fluorescent sensing, drug delivery, photodynamic therapy, tissue engineering and electronics, and these I call the biomedical facets of this application. So in acknowledgement, I would of course like to tell UTM and Ministry of Higher Education of Malaysia for various financial grants to inspire this kind of research, to motivate us. We are having in a large research group. Ibn Sina Institute of Sustainable Nanomaterials is one of that research group, very strong research group where I am working. Laser centers and my many students, postdoc student, Dr. Ali Akil Salim from Iraq, Mahmoud from Yemen, Dr. Hazri Bakhtiar from here, and Safwan, who are the main in our group, and they have developed different facilities over the years. And I am very much grateful again and again, I tell organizing committee for this opportunity, for the dissemination of the knowledge at free of cost. So we can share our knowledge, we can go forward, we can grow, we can motivate the industry for bigger investment to pursue, to forward our research. Department of Physics, Faculty of Science, I would like to especially appreciate their encouragement for this research, and Laser Center and our university research laboratory where all kind of high performance instruments are there for the characterizations and so on. So thank you so much for this opportunity. Thank you very, very much for listening.